Okay, welcome to this next installment of the IB Chemistry Standard Level Curriculum for Tracy High School. Today we're going to cover topic 10.3 of the IB rubric, which is covering the topic of alkenes. We're going to keep it fairly simple in this discussion. The alkenes, if you remember, are compounds that contain a carbon-to-carbon double bond. And so we're going to keep it fairly simple. We're going to use these two carbon versions, which would be called ethene. I may even throw in a few of the three carbon versions, which would be called propene. So most of my examples will probably be using ethene. I may throw in a few propenes, but again, all the reactions will behave very similarly. So you can probably just apply your reasoning skills. I think IB specifically wants you to know about ethene, so that's going to be most of my examples, if not all. Now, before we continue, please review the curriculum points. I'll separate these out. Each page will be dedicated to one or a couple of them. So some things to comment on before we begin. What we're going to be dealing with is something called an addition reaction in all of these examples. An addition reaction is a reaction across, the phrase is that it's a reaction across a double bond, or across the double bond. Now, the concept here is that whatever chemical we are going to react with this compound that has the double bond. For example, we have this ethene compound, and we're going to react some chemical with it. I'll just make a chemical up. We'll call it X, and this is a diatomic molecule. What's going to happen is that that chemical is going to add across the bond. So half of it will attack the one carbon, the other half will attack the other carbon. So you would see something similar to this. Now, of course, the ethene compound had two additional hydrogens, which I left off for simplicity. But excuse me. Notice that the compound added across. The electrons involved in the reaction were the two that I circled here. One of those electrons took part in this bond. One of them took part in this bond formation. That is an equal splitting of this bond. That's called homolytic fission. It's not really something you need to know about this particular thing, and it isn't necessarily how it always occurs when we study the actual mechanism. But it's a good way of thinking about it. It is a process in which that bond is shared equally. So that's what adding across the bond means. All of the reactions you're going to see are that type. They are addition reactions in which something is added to, it is added across the bond, and in addition to that aspect of an addition reaction, it also includes the processes where the two chemicals involved in the reaction are combined. They are added together. So that's what we'll be seeing here. In these addition reactions, they are adding across the bond. So the compound is being split equally, and the final product is a combination of the reactants. So let's go ahead and move forward. This first one we're going to specifically talk about are the first 2 points here. We're going to describe some equations, using equations, the reactions of alkenes with hydrogen and halogens. We're going to describe using equations the reactions of symmetrical alkenes with hydrogen halides and water. So this first one here is where you could apply either ethene or propene because it makes no mention of symmetrical. The phrase symmetrical here is an example of compounds such as ethene, which are identical on both sides of the bond. So we're going to stick with that one here. I like to approach these in a chart-like way because they are all very similar. So if you look here, the reactions we're going to study involve this compound, an ethene, specifically an alkene, with hydrogen, also with halogens. Remember, halogens can be fluorine, chlorine, whatever. I'll use chlorine, and they are diatomic. Also, it's going to be with hydrogen halides, which is something like hydrochloric acid, or water, which I think we all know, H2O. So what I'm going to do is create a little chart here, or a little graph, I suppose, and I'm going to put the alkene ethene in the center, and we're going to branch off from this the four different categories we had. We had the reaction of hydrogen with the alkene. We had the reaction of a halogen, chlorine, or possibly bromine. I think IB does want you to know the bromination reaction specifically. So maybe I'll switch to bromine instead of the chlorine that we discussed earlier. So let me write that here just to remind us of that. We're going to also focus on the reaction with water and a hydrogen halide. So let's do this one at a time. The first one we'll study is the reaction of hydrogen. So I'm going to put the reaction, other reactant next to the arrow. This process, when you react hydrogen with something, is called hydrogenation. Makes sense? And as we said previously, the hydrogen adds across the bond. So one of those hydrogen atoms will be attached here, one here. This double bond will no longer be present. Now, say a few words about this double bond and the reactivity and why this occurs. If you remember, in a double bond, we have two types of bonds. We have the first bond being a sigma bond. That is a hybridized bond. That tends to be a stronger bond. The second bond, and the third, if there were a third, would be a pi bond. And that comes from, if you remember your study of the Vesper theory, this first bond is from overlapping orbitals which hybridize in shape. But the second bond, as an example, suppose that first bond here was a hybridized orbital. Now there are some unhybridized p orbitals remaining which are perpendicular to the bond axis here. So the electrons in these particular orbitals can be shared, so you might want to, typically you'll see some dashed lines in a book indicating that second bond, and it's in that area that we symbolize the electrons being shared, not in the orbitals themselves. Regardless, that second pi bond, that second bond is a pi bond, an unhybridized bond. It tends to be a little bit weaker. So that lends to the reactivity of alkenes versus alkanes. The reaction which splits the entire double bond is fairly uncommon because that would require quite a bit of energy. But that first bond is fairly susceptible. So adding hydrogen to it is one of the options. And it goes across the bond. And so if we just apply some basic reasoning, these two dashes indicate the original hydrogens. And these, I'll use a different color, would indicate the new added hydrogens. So in this case, we have created specifically ethane. Generally or generically, we've created an alkane. So this is a method of production of alkanes. You add hydrogen to ethene. We'll talk about a specific version of this. It's in the production of margarine. We'll talk about that in a few moments. The second category I'm going to discuss here is that of halogenation. So I'll use as my example bromine. Now remember, this could be any halogen, so it could be the X could be fluorine, chlorine, bromine, or iodine. Bromine is specifically useful because there is a specific reaction. Halogenation is the generic. There is a specific one called bromination, which is obviously the addition of bromine to an alkene. And this is a technique used to identify the presence of alkenes. So we'll outline that in a future slide here. But if you apply some generic reasoning here, this bromine, in the process of halogenation, is added across the bond. And so you end up with a symmetrical, again I'll switch colors here to show the added chemical, a symmetrical halogenoalkane. Sorry about that. This is a halogenoalkane. We have bromine groups on two carbons. So if we were to name this, we would call this 1,2-dibromoethane. You won't be required to name them. The numbers are necessary to indicate that they're not on the same carbon, for those of you who care. However, just understand, this is how you make a symmetric, I shouldn't have said that. You add across a double bond with bromine. One is added to each. Would work with any halogen. I'll just leave it at that. I don't want to get too overly complicated here. A third category is the category known as hydration, where we add water. This one requires a catalyst to help the process along. It's an acid, and the most common being sulfuric acid. I don't know if you'll be asked to memorize that, but if you are, now you know. This as a catalyst to help this along, and this is added across the bond. Now there are more than 2 atoms here, so there is how do we split water is always the question. And so in this case, the double bond is gone, and the hydroxide portion, the OH portion of water, is added to 1 carbon. These are the 2 remaining. Let me go ahead and retain our same system here. Sorry about that. The OH group of 1 is added there. The H of water is added there. And these are the original hydrogens. Now there is a rule known as Markovnikov's rule, which states which carbon the hydrogen will be attached and which the OH will be attached. However, because the curriculum point states that it has to be a symmetrical alkane, you typically don't even need to know Markovnikov's rule. So if you're interested in looking it up, you can do so. It is not required for the IB standard level curriculum. This process is called hydration for obvious reasons. You're adding water. It is a process in which we can produce, as you can see, an alcohol, specifically ethanol. So we'll talk about that in a future slide. And the last is hydrohalogenation. We will use specifically hydrogen bromide. You could use hydrogen chloride, but again, I'll stick with the bromides because IB does actually like to use them. But it is symmetrical. So we have 2 atoms here. It's a diatomic compound, so it adds across the bond. Excuse me, I'm already breaking with our pattern. It's early in the morning right now, so forgive me. There is the added hydrogen bromide, and we have our original hydrogens there. So those are the generic processes you're required to know. In a future slide, let me go forward one and show you the next point. Distinguish between alkanes and alkenes using bromine water. So bromine water, as the name indicates, is water that contains bromine. Well, bromine is brown in color. So bromine water is brown in color. So this is a test to determine the presence of an alkene. If you have an alkene present in solution, or present, if you added bromine to it, the reaction, I'll use ethene again as my example, the reaction we outlined on the previous page would occur where bromine is added across the bond. Well, this dibromine compound here, this 1,2-dibromoethane compound, is colorless. So therefore, this solution with the bromine is brown, obviously. And as the bromine reacts with the alkene, the brown color goes away. So that is a test to indicate the presence of an alkene. If there was an alkane present, like ethane, and it was added to bromine water, which is brown, the brown color would remain because there is typically no reaction. So that's what this bullet point is talking about. That bromination is a method of detecting alkenes. And the next point, it's a little small here, so I'll read it. You can always... Okay, I'm going to have to pause right here because I'm about ready to run into my 15-minute limit for YouTube. So I'm going to pause here and I'll come back and do a part 2, and we'll start with this polymerization of alkenes, and we'll go forward to the next slide.